Hey guys, today I want to introduce you to one of my favorite topics of all math. It's probably why I got into math in the first place, and that is simply studying sequences, which is a bunch of patterns of numbers and all that. I love looking for a pattern, trying to figure out what the next one is, and so we're going to do a lot of that today. So let's get started. So, a sequence is really not much more than a list of numbers. And if that list of numbers is going to be useful for us at all, it usually follows some sort of a pattern or rule. And so here's an example. We've got the numbers 1, 3, 5, 7, and 9. And the rule here is if we want the nth term, then we take n, double it, and subtract 1. So these numbers, 1, 3, 5, and so forth, they're called the terms of the sequence. And we would describe or 9 as, say, the fifth number, the fifth term in the sequence. We could write that as O with this little subscript 5. By the way, I chose the letter O. You can choose whatever letter you want for a sequence. They usually are abbreviated with lowercase letters, but anyway, I chose O because these are the odd numbers. And so the fifth odd number, O5, is 9. And we have a rule here for the nth term in the sequence. So if I wanted to know what the 10th odd number is, I could do that immediately by simply plugging a 10 in for n. 2 times n would be 20, minus 1 would be 19. That brings to mind two different types of thinking with regards to sequences. We have one set of thinking, which is explicit thinking, where we have a formula and we can put in a number and we can instantly find any number in the list. That's great. If I wanted a 100th number in the list, this would be a great way to go. But there's another type of thinking that you can do with sequences that sometimes is more natural. For instance, you might just realize, hey, the next number is 11, and then 13. 15 and 17 because you're going up by 2, right? You're taking the last number and adding 2 each time. That sort of thinking is called recursive thinking. And some sequences can be thought of recursively and some can't. Some can be thought of explicitly, some can't. And there are benefits, disadvantages, and advantages for each type of thinking. And so in this video, we won't get into a whole lot of that, but I wanted to introduce that idea to you. So I wanted to give you a brief introduction to a bunch of different types of sequences, some of the adjectives we might use to describe sequences. So probably the most popular type of sequence is an arithmetic sequence. Arithmetic sequence is like the odds that we just saw, where you add the same amount each time. So an example of that might be this sequence, 6, 8, 10, 12. And you can probably realize that the pattern is that we are adding 2 every single time we go up 1. Kind of related, and yet very different in how they behave, is a geometric sequence. In the geometric sequence, instead of adding the same amount each time, you multiply the same amount. And so here's an example of that. 1, 3, 9, 27. You might be able to realize that we're multiplying by 3 each time. Another type of sequence is called a harmonic sequence. This is where you're interested in the reciprocals, or the reciprocals have a more obvious pattern. The most common harmonic sequence is simply 1, 1/2, 1/3, 1/4, 1/5, and so on. Another very popular type of sequence is the Fibonacci sequence. Fibonacci sequence is set up by taking 2 numbers and adding them. So the most popular Fibonacci sequence is 1 plus 1 added together gives us 2, and then 1 plus 2 gives us 3, 2 plus 3 is 5, and so on. The Fibonacci sequence shows up in a lot of cool places in nature, and we'll study it in more detail. But another sequence is the factorials. The factorial is indicated by this exclamation point. So if you wanted to know 5 factorial, what you'll do is you'll multiply 5 times 4 times 3 times 2 times 1, which is 120. And that set of numbers, this is 1 factorial, 2 factorial, 3, 4 factorial, and so on. Again, all those are found by multiplying down until you get to 1. A lot of sequences are periodic, or parts of them might be periodic, which simply means they repeat with some sort of pattern. How many terms it takes to repeat is called the period. We saw this with complex numbers. When you have different powers of I, that is a repeating pattern. 1, I, -1, -I, 1, I, and so on. Kind of related to that, a special type of periodic sequence is a modular sequence. And a modular sequence is when you wrap around some number. For instance, if you're in music, you recite the modular sequence 1, 2, 3, 4, 1, 2, 3, 4, and so forth. In this case, we're wrapping around 4. Every time we get to 4, we reset and go back down to 1. And so that doesn't have to be 4. You can have moduluses of 12, which is what the clock does, right? Every time you go through 12 hours, you reset back down to 1. Variations of this also might have a start at 0 instead of 1, but any sequence like that's called a modular sequence. Another important idea with regards to sequences is a related idea called a series. And so a series is a sum or a running total of the terms of a sequence. And so an example of that here's the odd numbers that we had earlier. And if I was interested in adding up the odd numbers and producing a new sequence, that would be called a series. And so the first number would just be 1. If I added 1 and 3 together, I would have 4. If I added 1, 3, and 5 together, I would get 9. 1 plus 3 plus 5 plus 7 is 16, and so on. Happens that the running total of the odd numbers is another famous sequence that you might recognize. I believe these are all square numbers, and so that's kind of cool. If you're talking about a series, you may hear the phrase nth partial sum. For instance, you might want to know what the 8th partial sum of the odds is, and that would be 64, the 8th number in that sequence. We will eventually study sigma notation, and so here's another way of writing that. This would mean the sum from 1 to whatever number's on top here of this particular sequence. Again, we'll study that in a later video if you want. All right. So let's see this in action. Here is a famous series. These are the triangular numbers. And the reason it's a series is it is what you get when you start just adding up numbers. If we take 1 and add 2 to it, you get 3. 1 plus 2 plus 3 is 6. The bowling number, 1 plus 2 plus 3 plus 4 is 10. So that's the triangular numbers. They're called that because they form triangles, as you can see these dots have made. And so our first question simply might be, what's the next couple terms? And so why don't we generate a list of the next couple terms? We have a pretty simple rule to find the next number, and that's just to keep adding up numbers. So we've got, we added 2, we added 3, we added 4. So if we add 5, we should get 15, and adding 6 gives us 21, and adding 7 is 28. Adding 8 is 36. Adding 9 gives us 45. Adding 10 is 55. 11 is 66. Adding 12 gives us 78. So that sort of thinking, where we take the last term and do something simple to it, like adding in this case, that is recursive thinking. And that works great if you wanted to know, say, what's the 10th number in the list. The 10th number in the list, it wasn't that far into the future we could find it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th number in this list would have been 55. But this sort of thinking does not work very good if you've got to find, say, the 100th number in the list. Because I don't want to go 99 terms into the future just to find the 100th number. And so if we want to find the 100th number in this list, I think it would be good for us to take a little bit of time to form an explicit formula. If we can find the formula for the nth number in this list, then we can just put 100 in there and we'd have our answer right away. So there's lots of different ways to find patterns and rules and formulas like this. I mean, this is a popular enough one. You could easily Google it and find the formula if you wanted to. But there's a nice geometric way of looking at this that I wanted to show you. So here's the fourth number in the list again, right? 10 dots here. I'm going to simply make a copy of this and rotate it 180 degrees. And now if I line this up underneath here, we've got a nice rectangle. And the width of this rectangle is 4 because it was the fourth number. And in general, the nth number would have a width of n. And its height is 4 plus 1, or in general, n plus 1. And so I could find the area of that rectangle by simply taking n and multiplying it by n plus 1. Unfortunately, that would be twice the number I'm interested in, but that's easy enough to fix. We'll just divide by 2. And so rule for the nth number would be to take n and multiply it by n plus 1, and then divide it by 2. Or, as it's often written in formulas, multiply by 1/2. So why don't we test that a moment with our 10th number in the list that we found by hand, and then we should be able to use that to find the 100th number. So if we take 1/2 times 10, and 10 plus 1 is 11. 10 times 11 is 110. And half of 110 is the 55 that we had gotten earlier. And so yeah, our formula seems to be working. This isn't, of course, a proof, but at least it worked for that one. And so if we wanted to use it to find the 100th number in the list, we'll do 1/2 times 100 times 101. 100 times 101 is 1,010. And, I'm sorry, no, it's 10,100. And if we then cut that in half, we get 5,050. And so the 100th number in this list is Gauss's number, 5,050.